So in Science 10 and in Physics 20, we've discussed the concept of work and we've given you a definition for work. In Science 10, you would have learned that work is force times displacement. Physics 20, we added a cos theta to the end of that just to account for any case where the force and the displacement are not lined up. So in Physics 20, we're actually going to give you a slightly more powerful definition of work. And the work on an object can be defined as the change in its mechanical energy. So mathematically, this can be given as the work is equal to the change in energy. And this change in energy, as I said, is the change in the mechanical energy. So this is really the change in the kinetic plus the change in potential. So this idea is known as the Work-Energy Theorem. We don't use it a lot in Physics 20. We use it a little bit more in Physics 30. And even then, we use a bit of a simplified version of the Work-Energy Theorem. Now, let's look at some examples applying the Work-Energy Theorem. So we have police investigators. They're going to find an 11,050 kilogram sports car. It collided into a brick warehouse wall. They determined that the car's speed just before impact must have been 15 meters per second. The wall brought the car to a complete stop with considerable damage. Investigators also note that the wall barely moved with a displacement of 3 centimeters. So we want to find the average force on the wall. We want to find the force that the wall exerted on the car, the force that the car exerted on the wall, and the work done on the car to bring it to a stop. Now these can be done in any order. What we want to do is we want to use the Work-Energy Theorem. You could do this from a kinematics approach or a dynamics approach, which is perfectly fine, but let's look at it using Work-Energy Theorem. So let's actually find the work done in this scenario. So the work done is going to be the change in energy, which is just going to be the change in kinetic plus the change in potential energy. Now, we have no mention of any elastic materials, so we don't have to worry about change in elastic potential energy. And this car is going to be driving, we're assuming it's going to be driving on a flat surface, so there is no change in vertical height. So we can say that the change in potential energy is 0. We're going to say no change in height. Because it's not like this car is driving down a slope into the wall and changing height. We're just going to assume it's always on a flat level ground. So we know that the work done is going to be the change in kinetic energy, which is just going to be half mv final squared minus half mv initial squared. So we have our final kinetic energy minus our initial. Now we are told that this car comes to a stop. So we know that Vf is going to be 0. What this tells us is that the work is going to be negative 1/2 the mass times the initial speed squared. So what we are looking at here is we are looking at the work that the wall is doing onto the car. We're using the car's velocities here. So this is the work that's being done on the car, and when we're doing work, something has to do work on the object. In this case, it's the wall. So we're going to have this negative 1/2. We have that mass of the car. We have its initial speed. We're told it's going 15 meters per second. So what we're going to get here is we are going to get a large value for work. So we're going to get about negative 1.29 times 10 to the 5 joules. So this is the work done by wall on car. We get a negative answer. That's good, because when work is done on the car, it's going to slow it down from 15 meters per second to 0. When we have a decrease in speed, we said that is a count of negative work. So that's good, we get negative work. Now, if we want to find the force to that, we're going to assume that the force and the displacement are in the same plane. So what we can do is, if we know that the work the wall does on the car, we can find the force that the wall applies to the car to stop it. Because we also know work is equal to the force times the distance. Well, we know that the wall moved a grand total of 3 centimeters. So if we know that, we also know the displacement. So we know that this force, we know that there's a work of 1.29 times 10 to the 5 joules, and we're going to divide that by that distance of 3 centimeters, but make sure that that's converted into meters. So this work acted over this small distance. So if we do that, we're going to get a force of about 4.31 times 10 to the 6 newtons. So this is the force of wall on car. Again, it's negative. I guess what we're saying is this direction we've assumed is negative, which is fine. It doesn't really matter because we haven't specified direction. So we know that the force of the wall on the car is going to be this negative 4.31 times 10 to the 6 newtons. We also want to know what's the force that the car exerted on the wall. Now, somebody might want to do some fancy calculations, but why would you waste your time doing that? We know by Newton's third law that if the wall supplies a force on the car is going to apply the exact same force on the wall with the equal magnitude, just in opposite direction. So by Newton's third law, the force the car on the wall is, we'll say positive, we'll change the sign, positive 4.31 times 10 to the 6 newtons. So the force is equal, it's just in the opposite direction, which will account for it by the change in sign. That's it. Now, obviously if you were doing this question, we wouldn't be taking the time to stop and explain all these things. So this question can be done very quickly by using the work-energy theorem. If you want to do it a kinematics way, you could find the forces first because you have the mass, you have the velocity initial, you have the velocity final. You can use that to determine the acceleration, then you can find the force, then you can find the work. That's another way of doing it. This just cuts out a lot of the, well, no pun intended, this cuts out a lot of the work. But however you want to approach the problem, it's your choice. You're the physicist in command. Let's look at one more example. So this time we're going to add in a little fun. We're going to put in an inclined plane. So we've got a 3 kilogram box. It's moved up a frictionless inclined plane by a force parallel to the plane. So at the foot of the incline, the box has an initial speed of 2 meters per second. At the top of the incline, which is 8 meters above the ground, the person pushing the box has done 256 joules of work on the box. So we want to find what's the speed at the top of the incline. So what we have going on here, we have an incline. So we have a box. It's eventually going to make its way up to the top. So we're told at the bottom, we are told that this thing has an initial speed of 2 meters per second. We want to find the speed at the top. In the time, in this thing being pushed up, there's 256 joules of work being done. We're also told we have a vertical height difference of 8 meters. So we would like to use the work-energy theorem to help us out here. So we know by the work-energy theorem states that the work done is just the change in energy, which is just going to be the change in kinetic energy plus the change in potential. So the change in kinetic energy is going to be half mv final squared minus half mv initial squared, because this is our final kinetic energy minus our initial kinetic energy. So this takes care of the delta EK. And then our change in potential energy we know is just mg times the change in height. So this takes care of delta EP. We know all of this stuff. We know most of this. We know the work, and I'm going to just put that term here. We know the work, we know the masses, we know VI, we know mg and h. What we want to find here is we want to find this VF. There's a few ways to approach it. First of all, let's get this half mvf squared by itself. So we're going to take this negative 1/2 mvi squared, we're going to put it on the other side, and we're going to take this mg delta h, and we're also going to put it on the other side. So what we're going to get is we're going to get this work plus 1/2 mvi squared minus mg delta h. This is going to be equal to half mvf squared. Now some people might want to be tempted to cancel out mass. Careful. Yes, there's a mass term here, here, and here, but this doesn't have a mass term on it. You cannot cancel a term unless it's present in every single term. So we can't do that, unfortunately, in this case. So let's solve for this half mvf squared. So half mvf squared is going to be this work, which we've been told is 256 joules. We have this 1/2, this mass of 3 kilograms times this initial speed of 2 meters per second squared, and then we're going to subtract off this mass times 9.81 meters per second squared, and then that change in vertical height of 8 meters. How you want to do this, if you want to rearrange this whole thing for VF and solve, go for it. There's no preferred way to do it. Sometimes it's easier to break things up into chunks, but again, it's your call on this one. So let's see what we get here. So I'm going to get it's about 26.56 joules. Keep in mind to add these terms, they all have to be in the same unit. So this is in joules. This is only going to work if this is in joules. And we know our terms for energy are also going to be in joules. So I know that half mvf squared is going to be equal to this 26.56. So VF is going to be this 2 times 26.56 joules divided by the mass square rooted. So we know this term. We have our mass of 3 kilograms. And then we're going to square root this whole mess. Like I said, how you get to this point, it's entirely your call. There's several different ways of doing it. So what I'm going to get here is I'm going to get about 4.20 meters per second. So what this is saying is that based on the information provided, if you're starting at 2 meters per second at the foot of the incline, you push it up 8 meters vertically on an incline and exert 256 joules of work. By the time you get to the top, this box will have a speed of about 4.20 meters per second. So that is our best way. That is another great way of applying the work-energy theorem. It's a really powerful tool. It's a shame we don't use it a lot in Physics 20. But like I said, you'll see it more in Physics 30 when we get there.